and both of the routers are connected with AS10102 in two different locations, one in London and one in Dhaka. So, customer routes are traversing through high latency or pingless links. The customer is connected with AS10102 in multiple different locations. The customer's Asia Pacific destined traffic from Dhaka is traversing high latency London router, then going to Singapore. The traffic route is going from here to London and then coming back to Singapore. The customer's European destined traffic from Dhaka is traversing high latency Singapore router, then going to London. The European area's routes destined rather than going to London. It's going through Dhaka, then Singapore, then London. Customers' Asia Pacific destined traffic from London is traversing high latency Dhaka router by going to from here rather than using this direct link. The connectivity is going from this London, Singapore, Dhaka, and then customer's router. So this might happen time to time if you are not using and choosing the specific prefixes which should have higher preferences in through which link. So the return traffic is not exiting the network efficiently. This is one more problem. So the customer is connected with 10102 in Dhaka and London both. Then the customer is also connected with another connectivity provider, ASY in Dhaka, and customer is advertising the same prefixes across all upstream from both the routers in Dhaka and London. Customers' Dhaka destined traffic from London router is coming through customer's London router instead of upstream Dhaka router. So when the customer's traffic destined to this router, actually this from London, it should traverse from London, their London router, and then it should come to Dhaka. But rather than there, it is actually taking other specific routes. And the customer cannot actually change the local preference because changing it causes all its traffic moved to the other service provider ASY. Then comes return traffic load balancing. How can you load balance in between the return traffic for a specific location? Because the customer is actually connected with two different providers. One is 10102 and one is AS6453 in both London and Dhaka. So as the customer has direct connectivity with AS6453, customer doesn't want its Asia Pacific traffic return from Dhaka router to come through AS10102 or this router. And customer doesn't want its European tagged return traffic from Dhaka via the other provider as they have better latency through other tertiary provider, this direct connectivity. Then there is a remotely triggered black hole route. We do have to face DOS attacks or DDoS attacks regularly. So let's say you are being hit with a DOS attack and it's 1 o'clock at the night. So sometimes you cannot get all the higher officials who can actually do a black hole routing for a specific prefix or maybe one of your IP addresses due to which you are facing the DDoS attacks. So how can you take care of it by yourself? Because what happens is when you are attacked using a DDoS attack, you will see that most of your backbone links get saturated. No traffic is going in and no traffic is going out because you are being hit with a much more bigger pipe of bandwidth than you have to the internet. So what happens is you need to somehow inform the upstream provider or your transit provider to let them know that this is the IP which is being hit by a DOS attack or a DDoS attack. So what does the upstream do actually? They just do a specific null route for the specific IP address or maybe for the prefix if you have multiple IP address. So what is the possibility like of if you had the control, you actually didn't need to wait for it and to communicate with your upstream provider and wait for them to take care of nulling the route. So here we will do some analysis of one of the tier 1 providers standard BGP communities. So they accept standard BGP community, there is no export and no advertise. No export is like when you do not, if you have the no export BGP community stacked with a prefix, that means that this prefix will not be advertised outside of your AS number. If it is a no advertise, that means that this prefix will not be advertised outside of the specific router. Then you can do some local preference adjustments. So if you send specific communities, it will accept local preference of 70, 80, 90, and 110. The standard customer routes is 100. The standard for peer routes is 90. There is nothing defined for the transit routes as they are a transit-free operator. Then they have also a mitigation of DDoS attacks or RTBH route. They accept /32 prefixes, and if you attach the BGP community 64999:0, I don't know why they use a private AS number for this, but they could have used 6453:02. So if you send a /32 IP prefixes, or I don't know, like if they have something for the IPv6. So what they do is they do a local null route to that prefixes and advertise it within their network. So you are not being exhausted with DDoS traffic in your network. So how do your routes get distributed to peers? So if you send a prefix with a BGP community of 6500N, where the N stands for 1, 2, or 3, AS number, what happens is it prepends their AS number 6453 N times to their peer ASN number. Okay, so this AS number is, let's say it is 10102. So if you're advertising a specific route with 65003:10102, what happens is while your route is being advertised to its upstream or to another of its peers who has got the AS number 10102, your specific prefix will be prepended with AS 6453 for thrice. For 65002, it will be twice, and for 1, once. And if you do not give any, then it will not be prepended. If you give the BGP community 65009:10102, then it will never redistribute your prefix to other peers which has got the AS number of 10102. Then there is a 6500N colon 0. That is, if you want to prepend AS6453 as many once or twice or thrice to all of its upstream, all of its peer providers. And 65009 colon 0 is do not redistribute to any peers of its. So your prefixes will not be advertised out of AS6453. It has got some informational community. The peer routes are classified as 6453 colon 86. There is nothing defined for their customer routes, nothing defined for transit routes as they are transit-free operator. Geographical information are encoded with the 4 characters with limited visibility. So, what is the solution of the first problem, the inbound load balancing? Changing the local preference on one link, but local preference does not traverse across different AS numbers. So what happens is BGP path attributes, there is weight, which is with Cisco proprietary, and there is local preference. But what happens is local preference is not actually carried over different AS numbers or different routers. So upstream needs to be changed to the local preference while configuring the BGP inbound route policy. But upstream can set the local preference based on conditional BGP check, community check. So what happens is the upstream actually will not, your set local preference will not be changed when a prefix is being advertised to its upstream provider. But what happens is the upstream tells you that if you set a BGP community specific to these, I will check whether if a prefix of yours is being tagged with that specific community. If so, what I will do, I'll just change the local preference of that prefix to a different value, like 80 or 90 or 100. Can you see it? I'm not sure. Okay, so this is a configuration example from iOS XR, Cisco iOS XR. So we are creating a route policy called customer in. So the customer is advertising a specific prefix with 10102:75. Then what happens is I will check all the routing advertisement from a client or a customer, and if I see that if the customer is sending a prefix with 10102:75, I will change the local preference to 75. Then I will check if it is :85, then I will change the local preference to 85, 95, and 105. And if there is no match, then I will do nothing. I'll just skip that prefix to change the local preference. I will not need to touch the local preference of that specific prefix. So This is actually the configuration of similar to that in this iOS XR. iOS XR is actually much more our language oriented rather than the Cisco iOS one. It's a bit like you have to create the IP community list, then you have to create the route maps, then you can change the local preferences. But in the iOS XR, actually, it's much more easier to configure. Okay, so what happens is the customer router in the London link. Okay. Here is the London link towards customers. So the customer is actually permitting all the prefixes that you want to set out towards this location. So what happens is the customer is advertising one different specific prefix in Dhaka and one in London. So the customer knows that one of its prefix might have better visibility and better route output towards using the Singapore and Dhaka link. So what happens is when it is advertising its prefixes towards London, it is actually reducing its local preference or increasing its local preference, and that's how actually it is load balancing the traffic in between the London link and the Dhaka link. So on one side, it is actually reducing the local preference to their London router. So what happens is unless otherwise the customer has much more traffic coming and originating from London, this link will be less used rather than the user's Dhaka link. Then there is outbound traffic preferring much more expensive links. The upstream has actually two different tasks to do here, changing the local preference. Like the transit routes will have a local preference of 90, while for the public or private peering, local preference will be 95, and if it has the customer routes, local preference will be 100. So how can you actually use BGP community to isolate routes? The transit routes, the first digit of the second octet is 1. For public or private routes, what we are doing is we are changing the first digit of second octet to 2 or 3, and the client routes is first digit of the second octet is 4. Okay, so what happens is in BGP community, rather than considering the communities as numbers, it is much more easier to compare them as strings, because it is much more easier to handle rather than calculating the numbers. So we are talking about only the first digit and not the other rest of the digits. So if we change the first digit to 1, that means that the traffic actually is a transit route. If the first digit is 2, then it is a public peering route. If it is 3, then it is a private peering route. If it is 4, it is a client route. So I'll come more into the details of how we geotag the routes. So for our Dhaka router, what we did was we actually added a community called 41011. So when the routes are coming from a customer, we are adding this route policy, set community 10102:41011. There is a specific value of 1011 for Dhaka routers. I will define it much more in little slides. Then there is, if the customer's route, we are not changing the local preference because we are using a default local preference of 100. So if we are peering with a private peer, and while we are accepting the routes using a BGP advertisement, what we are doing is we are applying the route policy private peer in. So what happens is we are setting the community to 10102:31011, so that the 3 actually stands for the private peering, and we are changing the local preference to 90. You remember that for transit provider, it is the lowest 80, but for the other peerings, we use 90. For any public peering point to the for BGP peering, we are using the policy public peer in, where we are setting the community to 21011. 2 stands for public peering. And we are changing the local preference to 90. And if we are connecting with a transit provider, we are setting the local community to 10102:11011. So 1 stands for that first one, that is the transit provider, and we are changing the local preference to 80. So we have still 4 digits to work with, the last 1011. So on a later slides, we'll actually show you like why and how we are going to do use that tag. So outbound traffic are preferring more expensive links for the customer. So upstream has defined optimized outbound routing, but customer has to route selective traffic up to the upstream's router, because if you cannot route a specific traffic to your upstream, the upstream cannot forward it to somewhere else. So the local preference actually rests to vendor neutral default value across AS numbers. So here there are 2 different community lists we are creating, that is 100 and 101. So one is the first one. Here a bit cryptic writing, but what happens is 10102 colon this part only 2-3. It is actually in between a square braces. So what happens is this value can be either 2 or 3, and then there is this dot 4 within curly braces. This means that after either 2 or 3, it can be 4 different characters or numerical digits. So then there is another IP community list, that is 10101. For this, we are trying to match 10102:1, then any 4 digits. So if you look at this, so if we want to match BGP community with is 4 digits, and this is also 4 digits. So we have to match with either 2 or 3, and then any 4 digits. So this is what we are actually doing in community list number 100 and community list number 101. So what happens when we match a community of 100? When we are matching a community of 100, we know that the upstream provider is providing us with prefixes which are originating from a public peering point or a private peering point. Either it might be any commercial peering point like Equinix, DECAX, or AMSIX, something like that, or they might have some private peering with other organizations within their country or somewhere else. So whenever a traffic that is coming with a 5-digit value starting with 2 or starting with 3, that means it's a peering point route which needs to have a local preference of 90. And if it is coming with matching the community 101, that is anything starting with a digit of 1, that means it is actually a transit route. So transit routes are much more expensive for everyone. So what we are going to do is we are going to lower the preference to 80. Okay, if you remember the picture from here, so what happens is there is one more service provider, that is ASY, but it is not connected to any public peering point like London IX or Equinix IX or in Bangladesh PDIX. So it has got only one upstream to internet, and it has got a transit routes, all transit routes. So that's why what we are doing here is while we are receiving the prefix from ASY, what we are doing is we are setting all the local preference to 80. So now what happens is the transit routes both from 10102 and from ASY have the same local preference 80. But now let's say you know that if you need to go and connect to any specific routes from a local IX which will actually give you much more better performance, you know that AS10102 has tagged and identified those routes in a different manner, so that whenever you need to go to those prefixes, your outgoing request should go through 10102 rather than ASY, because AS10102 is providing you with much more information on the prefixes, so that you know how to go and how to touch the prefixes and routes from the peering providers. So whenever from this router, Dhaka router, you are trying to go to Equinix, you will actually have much more better output visibility using this Dhaka router than going to Singapore router and then going to either Equinix or maybe go directly to London and then going to London IX. So outbound traffic preferring higher latency links. So upstream is tagging routes based on its origin as follows. So you remember the value 1011, right? So what happens is this second value, this is the second value. So this value will actually vary from 1 to 7. So if the second value is 1, the second digit of the second octet, then you know that the routes are originating from an Asian location. If the value is 2, then the route is originating from African region. If it is 3, then it is Europe. For 4, it is North America. For 5, it is South America. For 6, it is Australia. For 7, it's Antarctica, although there is actually hardly any chance that there is any upstream providers working in Antarctica. But again, like as you have the option, you can actually tag, like this might be actually one option. This is just an opinion, but you can actually redesign your geocoding with these last 4 digits. So as you remember that we were using 2 or 1, the first digit, and the last 4 digit we are using 1011. So the second octet actually means that whenever we are tagging, Bangladesh is lying in Asian region, so that is why we are using 1. So we are actually changing the configuration here, like how that is why we are actually tagging with 1011. The PR configuration, it stands for 21011 additive. Then for transit 11011. For client, it is 41011. Okay, for Singapore, we are actually changing the last value with rather than 1011, we are using 1021. So the country code actually changes from 1 to 2 for Singapore. Then for London, it is 3011. So 3 stands for Europe. There is Brexit going on, so I don't know where London will fail after that. So maybe we have to change it. So how does the customer actually use this information to change its outbound routing preferences? So let's say the client is actually sitting in its London router. The client is using Cisco iOS. So we are permitting 2 different community lists in London, that is 100 and 101. Community list number 100, which is permitting 10102 colon. So the first value, that is 1-5 within a square brace. This means that the first value can be either 1, 2, 3, 4, 5. Then the second value must be 1 and then any 3 digits. This means that we are actually choosing the routes from Asian region, and the IP community list 101, which is mentioning the second digit as 3. 3 stands for 3 stands for Europe. So as the customer is configuring its London router, so what happens is it is actually choosing in between the Dhaka routes and in between the 10102 links from its London upstream. So we are using one route map that is from AS10102, in where actually they are setting the weight to 1000, and where it is matching the community 100, and it is also setting the weight to 1000. So whenever the client's outbound traffic will go to prefixes originating from London or originating from Dhaka, it will actually use two different links. The same thing actually stands in Dhaka router for customers originating routes in different links in Dhaka, and from the prefixes of originating from Dhaka, it is actually matching and changing the local weight. So here is actually some real life example, and this has been a debate where actually it really gives you some added advantage. But while actually I was working in this organization, I used this sort of setup, and I think it gives us some better results. So this was our scenario. We were using as Tata Communication actually used to use for AP region, they used to have a tag called 64.6453:3000. Then for EU, they used to use for 2000. We take these prefixes and we try to do some trace routes from different locations and different values. So while it is 6453:3000, if you check the default BGP table and using trace route, we have the trace route result of 632 milliseconds. We are having 6, 7, 10, 11 hops. 1041.4.1 was actually received with a BGP community tag of 6453:3000. That means that this prefix was being originated from somewhere in Europe, in AP region, Asia Pacific region. So, and then this is something using the London link of us, and if you see, it is like around 530 milliseconds. So a bit better from 632 milliseconds. But after we have changed the routing policy to match this, what happened? The trace route report actually gives us 259 milliseconds only, which is actually a 50% reduction of the latency. And like if you see, like the traffic is going to where I think directly Australia or somewhere using some longer link, but it gives us much more optimized traffic in Australia using the Asia Pacific routes of. So actually, what did we change? So this was our routing policy. If source in 270.9.255, that means if we are 270.9.255 was actually the IP address of Singapore router. and community matches any of AS6453-AP. AS6453, the community list of AS6453-AP actually includes 6453:3000. Then what we are doing is we are setting a wait to 2000 for those specific prefixes while we are receiving those routes from our Singapore router. So if it matches, then we are changing the wait. If not, then we are done. End if, and end policy. So here is case number 2 for the prefixes. So here we are actually choosing a prefix 1.8.52.1. You can see 6453:2000. No, I'm not sure. So within the default BGP route table, we are getting around 306 millisecond. And after route policy, we are getting 172 millisecond. (306), 172, nearly half of the delay. So what is the configuration we changed? This was our routing policy. If the source is in 182.16.142.0, which is actually the IP address, the loopback IP address of our London router, and community matches any AS6453-EU, that is 6453:2000, then we are setting the wait to 2000. And so whenever the traffic is going towards London and matching these prefixes, we are actually getting a much more better trace route results and better latency, like dropping from 306 to 170. That should be a much more optimized route from my point of view. So in both cases, actually, we had lower latency, then lower hop count, and better performance. So any questions so far? Okay, then we will go for a tea break, and we will come back for the rest of the session.